Take a look at page 3. Like I said, we don't need to worry about the redox reactions because we're not responsible for them. We're going back up to the top. Now, I did pause the video at a couple spots to talk about the charge. We saw the symbol of alpha, kind of looked like the fish. Beta was my B with the very long back. And gamma was my Y. Now, charge isn't particularly important. We will talk about a couple of them. When it comes to alpha, the release of an alpha particle is a supercharged helium molecule. What we find out is that when our isotope goes through alpha decay, at the time of its half-life, it will eject a helium atom. We also give it a +2 charge. Now, we saw that in the video that the penetrating power is incredibly slow. It's incredibly weak. Alpha particles typically do not last great distances. After a couple centimeters, it really loses all of its get up and go. So we saw that it can't pass through paper. It's incredibly weak. Now, we have out, I hope that everyone here has a fire alarm in their house. You check it once a year. But like the video stated, there is a small bit of and some of smoke alarms holds a small amount of a small collection of isotope 241, where it releases alpha particles. When the alpha particles are not absorbed by the detector, instead absorbed by smoke, carbon dioxide, then that alerts the system that there's a lot of smoke in the area. And that's when it starts chirping at you. We have small things like this all the time. Now, when it comes to beta will either come as a -1 or a +1 charge. The charge is not important. What is important is that what's being ejected off of the isotope, and usually it's a high energized electron. Now, these have a little bit more power behind them. Usually they're able to make it through. They're stopped by items, by metal items or thick concrete. Who here has ever had an X-ray done before? Anyone ever had an X-ray done? How can I pass energy in order to see what the bones look like inside of me? They're not alpha particles. They're beta particles. Fast enough to pass through your skin, but weak enough to be stopped by the detector. Gives us a chance to see what's going on the inside. Also, can be used as you get older. There's some procedures that you're going to have to do where they're going to have to be able to track your metabolism inside your body. Another good source of beta particles being used in a medical procedure. Radiation is not terrible for you as long as it's, like the video said, regulated. Unregulated radiation is what gets you. Who here flies a lot? You ever been in an airplane before? Once or twice? You know that the further you get away from the surface of the planet, the more radiation your body absorbs. Flying gives you, I believe it's every 3 hours. It's the equivalent of standing in direct sunlight for 4 hours. Not a lot more radiation than you normally would ingest on a regular basis, but more than what you would expect. Gamma is, excuse me, our fastest, and it's just high energy light. There is no mass to light. And it is the most penetrative. When we think of scary radiation, we think of gamma. Marie Curie, one of the founders of what we know as quantum chemistry, quantum theory chemistry today, and also in realms of physics, was one of the forefathers for this. Because she was one of the forefathers of our understanding of radiation, unfortunately, like the video said, her laboratory is still radioactive to this day. She sits in a lead coffin, a lead tombstone, and if I remember correctly, she was also exhumed, and 6 feet of concrete was poured around this lead capsule to prevent her radioactive remains from poisoning the grounds around her. She will remain radioactive to around 2150. More than 100 years from now, her body would eventually get to the point where the radiation the radioactive decay that's rolling off of her corpse is to normal levels, or what we would consider normal levels. She passed away at the turn of the last century. I think she passes away 1911. Her body would not be a danger to the surrounding area for almost 200 years after her passing. The work that she did is the ground that we build a lot of things off of. Very cool, very weird. Science is crazy. Half-life. We picked this up in the video. This is the time it takes for half of radioactive isotope to decay. The half-life is the time it takes for half of the radioactive material to decay. Now, my question to you, some of us took Earth Science last year. Can you see a hands who took Earth Science last year? One person? Just one? Who took biology last year? Oh, so you guys do know about half-lives then. This is good. Now, in the video and also in your biology class, we talked about carbon-14 and its ability to help us with absolute dating. If you were in Earth Science last year, we talked about some other isotopes that have longer half-lives that we use to identify the absolute age of rocks that we pull up from the ground. So let's go ahead and take a look at our 3 questions here. Isotope cesium-137 has a half-life of 30 years. I start off with 1.0 milligrams of substance. I need to figure out how much remains after 90 years. If my half-life is every 30 years, and I'm trying to figure out how many half-lives have happened in 90 years, I can do simple. 90 divided by 30 gives me what? 3. So that means that 3 half-lives have happened. Everybody see how I got that? So if my first half-life, so at the beginning, I start with 1 milligram. After 30 years, half of that material breaks down. So what's half of 1? What's half of 1? Give it to me in a decimal. 0.5. 0.5. That was 1 half-life. In 30 years, 1 half-life goes off. I go from 1 milligram to 0.5 milligrams. Another half-life goes on. I'm at half. I'm at 0.5 milligrams. What's half of 0.5 milligrams? 0.25 milligrams. After 2 half-lives. 30 years, 60 years. That means we got 1 more half-life to go through. And I'm going to draw the arrow up for this one. 0.25 milligrams. What's half of 0.25 milligrams? 125 milligrams. That's how much material remains after 3 half-lives. Does the number look like it ever really gets to 0? No. Radioactive decay is a forever thing. It'll keep reducing itself down and down and down and down, but never quite hitting 0. So, you're going to help me out a little bit on number 2. And also, I'm going to have you finish off number 2. So, we have 2.5 gram sample of strontium-90. Was formed in the 1960 explosion of an atomic bomb at the Johnson Island in the Pacific testing site. So now we're talking about hydrogen bombs and the fun things that they were. The half-life of strontium-90 is 28 years. I started with 2.5 grams. And we'll figure out what year it was when I reached 0.625 grams. So I need to figure out how much time has passed to go from 2.5 to 6.25. Now, using your knowledge that a half-life is the time it takes for half of the material to be broken down, I want you to figure out how many half-lives it takes to get from 2.5 grams to 0.625 grams. And I want you to write that on a whiteboard. So, person at the end, we'll give you a hand here. If you can grab yourself a marker and a whiteboard, we'll pass things down to everybody else. There we go. Now remember, ladies and gentlemen, I don't have enough erasers for everybody. But I want you to tell me how many half-lives will you have to go through to get from 2.5 grams to 0.625 grams. That is your goal today. Multiple goals today. One of the goals today.
Yeah. So we're trying to figure out how 2.5 becomes 0.62.
How many more? 2?
3.
3?
So how many half-lives has soy? Okay, so maybe we can set up well.
What's half of 2.5, guys? I know you guys can use a little bit of division without a calculator. I have faith in it. I have. You guys are killing me on my view of you guys. If we can't do a little bit of division, just a wee bit. Physical pain. Absolutely. Derek, I know you're not pulling out a phone right now, my friend. Okay, ladies and gentlemen. Let's do a little bit of practice real quick. So 2.5 divided by 2. How many times does 2 go into 2? 1. How many times does 2 go into 5? 2, right? 2 times 2 is 4, right? 2. So leaves 1 remaining. Put a space there, because obviously we got a remainder. We got to get rid of it. 2 goes into 10. How many times? 5. All right. So 1 half-life, I go from 2.5 to 1.25. All right. Let's do it again. 2 divided by 1.25. Does 2 go into 1? Does 2 go into 1, ladies and gentlemen? It's a yes or no response. I don't understand the head shaking. I don't know if you're having tremors or you're shaking your head at me. Does 2 go into 1? I need a verbal response. No. Thank you. Does 2 go into 12? How many times does 2 go into 12? 6. How many times does 2 go into 5? 2. 2 times 2 is 4. How many times does 2 go into 10? Look at that. Oh. How many half-lives did I go through? 1, 2. So, I go back here. I've gone through 2 half-lives. Now, each half-life takes 28 years. I need to figure out what year? So this was formed in 1960. So my next question is, if I went through 2 half-lives, how many years have passed? 2 times what? What can I pull from my question to tell me how many years it takes for a half-life to go through? 28. So 2 times 28. 16, 1, 4, 56 years have passed. So I didn't ask how many years have passed. I asked at what year do I get 0.625. So I need to add 1960. That's the year that was created. Plus 56. 6. Oh, wait. Am I doing this right way? I don't do this right way. We'll get answer of 2016. The year that my 2.5 grams of strontium-90 that was formed at an atomic explosion site in the Pacific testing area, I will get 0.265 grams of it in the year 2016. I'm gonna put a timer on the board. I want you to answer number 3 by yourself. A half-life of plutonium-218 is 3 minutes. How much of 0.2 gram sample will remain after 15 minutes? I'm going to give you 4 minutes. All right, do me a favor. I want you to write your final answer on your whiteboard. What is the final bit that remains after the 15 minutes? On the whiteboard, ladies and gentlemen, on the whiteboard. Make sure you're writing your final answer on the whiteboard.
Jackson, what's your shirt say? Oh, it's Universal. Oh. I don't know. I saw E.T. and Back to the Future. I was very confused what was going on. Like, throwback to the 80s, but appreciate it.
I know it's.
All right, let's see what you guys got on your whiteboards. And that's 3, 2, 1. Let's see what you got so far. Looking good, ladies and gentlemen. Looking good. Looking good. A good start there. Good start. All right, we got some interesting ones there. Interesting ones. Ladies over here, what we got? How do you see a whiteboard in the air? I don't want to see nobody without a whiteboard in the air. Perfect, perfect, perfect. Waiting on the 2 back there. You never got a whiteboard. Are there not any whiteboards in that row? There should have been 7 of them. I gave you markers. What are you doing with my markers then?
They don't even work.
You tell me now?
That's what I think. Don't tell me mine doesn't work either.
I appreciate you telling me. I have extra markers. Give me a quick second. All right. How many half-lives did you have to go through? How many did you count? What's that, Valeria? There you go. There were 5 half-lives you had to go through. How do we calculate 5? Well, we know that the half-life is 3 minutes, and we had 15 minutes to go through. 15 divided by 3 gives me 5 half-lives. Now I start off with 2.0 grams. How much do I have after 1 half-life? 1, right? What's half of 1? Half of 2? 1. Second half-life, what's half of 1? 0.5 grams. Third half-life, what's half of 0.5? 0.25 grams. What's half of 4 half-lives? 0.125 grams. We break it down one more time. 0.0625 grams. It'll keep getting smaller and smaller and smaller, never going to 0. So, this is everything that's going to be on the test that you're going to take on Thursday. If I go back to the beginning, balancing my equations, identifying what type of reactions you're going to see, identifying products, identifying what type of reaction you're going to see, followed by balancing said reactions, and 2 or 3 questions about radioactivity. For the radioactivity, I would focus on two things. I would focus on the symbols, I'd focus on penetrating power, and I would focus on my ability to determine the half-life of something. Or if I'm given the half-life, being able to tell me how much remains after something. Half-lives you saw in 7th grade in life science, which I know because I was there for for most of us here. You talked about it in 8th grade, physical science, your intro to chemistry physics class. I don't know if you talked about it in intro to environment, but I can guarantee you that you saw it in biology. I guarantee if you saw it in earth science. The only ones I can guarantee are the ones that I've taught. We're not adding anything new to it. Maybe the symbols. I know at least when we were in biology last year, we did not talk about the 3 symbols of the different types of radiation. Now, time is a little bit pressing, so I'm going to give you 2 things for homework. Number 1 is your reactivity of metals lab. Now, for those who were not here for the reactivities of metals lab, you're going to want to pick that up from somebody in the room. Because you cannot do the next step without first having a full table. Now, there was we were pretty quick with it, with collecting our data. So I do want to point out a couple things. The metal and the metal ion are 2 different things. The metal was what was the pure sample. So like samples 1 and 2, that was your copper wire. For samples 3 through 5, that was the zinc. 6 through 8, that was your magnesium ribbon. Now the metal ions what caught a lot of people. They were confused about this. Now remember, in your procedure, you had different drops, right? In well 1, you had lead 2 nitrate. Well 2, you had silver nitrate. The metal ion is the item that ion was that was in solution. So if I look at lead 2 nitrate, what's the metal ion? The lead or the nitrate? The lead is. So for well 1, the metal ion is lead. For well 2, I go back to my procedure. Well 2, silver nitrate. Silver nitrate, what's the metal ion? It's a silver, right? I'm going to do that for the other ones. Now, the observations you had to be there for. Now, as we know, not every reaction caused an observation. Some of them, nothing happened. Sometimes the metal changed colors, or it became foamy, or there was something growing on the original metal. If you observe something, you're going to write a balanced equation for what actually occurred. Because we had a pure metal, so A is my metal, B, C was my solution, with a single replacement reaction, where A replaced the cation of my item in solution, forming AC plus B. Example of this one would be observation number 2. Copper wire plus silver nitrate. We saw this grayish film begin to grow on the side of the copper wire. If not, you should have noticed it. So my question to you, what is copper kicking out? The silver, or is copper kicking out the nitrate? It's kicking out the silver. CuNO3 plus Ag. Now, I have to worry about my balancing. To give you a hand, copper is going to be in +2 form here. What is the charge on my nitrate? So I have a -1, a -2, or a -3 charge. -1. Do my charges cancel each other out? No. What do I need? Do I need more copper or need more nitrate? Need more nitrate. CuNO3, 2. So that's my skeleton. Now you'd have to balance that. Where you had an observation where something changed, you're going to write out that formula, predict the solutions, predict the products, balance that equation. Not every one of them had an observation. You're not going to do 8 of them. You're going to do like 4 or 5 of them. Now, because time is pressing, I'm also going to have you guys come up, everybody. And I want you to grab my quick check. You're going to bring this to me on Thursday. Completed. 10 points. First 6 questions. You're identifying what type of reaction it is. Questions 7 and 8. I give you the reactants. You're going to predict the products, balance the equation. 10 points. Easy. Everyone come up, grab a copy. So that means for homework, you're finishing the lab, you're doing the quick check. The quick check has questions that are similar to what you're going to expect to see on the test on Thursday. 10 points easy. Get it in, get it done.